we've studied discrete random variables and specifically binomial and Poisson distributions. We're going to now make the move into continuous random variables, which are values that have to be measured as opposed to counted. So some examples of this might be somebody's age, or their weight, or their height, or the speed of something, things like that. Those are not things that can be counted, but they're things that have to be measured. So some similarities between discrete and continuous random variables. They're used to model results of random experiments. They have probability distributions that describe the behavior and allow us to make predictions, and they have parameters such as mean, median, mode, all that fun stuff. Some differences, though. Discrete random variables have outcomes that have distinct values, whereas continuous random variables, the outcomes have to be measured. They're not distinct. They're not countable. For each value of a random variable in a discrete distribution, there's an associated probability, where that probability for each event is between 0 and 1. With a continuous random variable, we can't talk about the probability at a specific value. That probability is actually always 0. We're always going to be looking at the probability that our variable is between two numbers. And the characteristic of discrete and continuous random variables are different. And they must be treated slightly different in how we approach and work with them. When we first studied calculus, we saw that we could find the area under a curve by making a bunch of little rectangles and discretely adding those up, and then we shifted to the idea of using an integral, which was more of a continuous thing. We changed delta x to dx, that sort of thing. With the shift to continuous random variables, we're no longer going to be adding a bunch of things up. We're going to be evaluating integrals and using calculus to help us find parameters. And for a probability density function, for a continuous random variable, it's going to be given to us as a function, and that f of x always has to be positive for all values of x in the real numbers. And if we integrate from negative infinity to infinity with respect to x, we will get 1. That is, the area under the curve, the total area under this curve has to equal 1. This is going to eventually represent probability for us. And what usually happens is we don't talk about negative infinity to infinity because f of x is usually only defined over an interval such as a to b. Well, we're going to see that in these examples. So we have f of x being the piecewise function, 3x squared if x is between 0 and 1 inclusive, and 0 everywhere else. Show that this is a probability density function. Well, f of x is greater than or equal to 0 for all x on the interval 0 to 1. So that's the first condition that has to be met. The second condition that has to be met is the integral evaluated at our two endpoints, 0 to 1, of f of x, so 3x squared dx, this needs to be equal to 1. So let's integrate. We get x cubed evaluated at 0 and 1. Substituting our limits of integration, we get 1 cubed minus 0 cubed, or 1. There's our second condition. Therefore, f of x is a probability distribution. Some properties. The expected value or mean. Remember, we saw this formula in the discrete random variables as the sum of x times p of x. Well, this time we don't have p of x as we have this function representing eventually probabilities, but we're going to take the integral from a to b times x times f of x with respect to x. The median will be where the area under this curve equals 1/2, because if we're talking about area under the curve is meaning probability, the median would be where half of the data lies below. The mode will be the values of x for which f of x has a maximum, well, duh. And the variance is the integral from a to b of x minus mu. Remember, mu is just a number that we calculated earlier. squared times f of x dx. Or similarly, you might remember this form, the expected value of x squared minus the mean squared, where the expected value of x squared is this. You can use either one, it doesn't really matter. Example time. Here's our probability density function, f of x, defined for 0 to 2. Find the expected value, that is the mean, the median mode, and variance. Let's start with the mean. The expected value would be integral from 0 to 2 of x times f of x. And, well, this can be simplified a little bit. We have 2x squared minus x cubed dx. That's a fairly straightforward anti-differentiation. We have 3/4 2/3 x cubed minus 1/4 x to the 4th, evaluated at 0 and 2. And substituting our limits of integration into this expression, into the antiderivative, what we get is 1. So we are having an expected value for this function, a mean of 1. Median. Let's find the median next. The median is going to be when we take this function and integrate it from 0 to some number that is going to be the median value. When this equals 1/2, when half of the distribution is located beneath it. And I forgot my 3/4. So we take the antiderivative. X squared minus 1/3 x cubed, evaluated at 0 and m equals 1/2. And we're going to substitute the limits of integration now. And what we get, and we're going to do 3/4 times m squared minus 1/3 m cubed minus 0 squared minus 1/3 times 0 cubed. And that, of course, becomes 0, but this equals 1/2, and this is going to be an equation that we solve. 3/4 times m squared minus 1/3 m cubed equals 1/2. Solving this, we get that m is equal to 1. So the median value for this distribution is 1. Okay, how about the mode? The mode is where f of x is a maximum. Okay, well, how do we... Derivative, that's right. So f prime of x is equal to 3/4 times 2 minus 2x and this equals 0 when x is equal to 1. So the mean, median, and mode are all 1. Wow, cool. We'll come back to that in a second. But let's lastly find the variance of x. So how do we find variance? Well, it says in the formula, it's the integral from a to b of x minus mu squared. So 0 to 2 of x minus mu. X minus, what was mu? What was the mean? It was 1 times f of x. So times 3/4 x, 2 minus x dx. And we can clean this up and expand, and we'll get 3/4 times the integral 0 to 2 of negative x to the 4th. I'm expanding this here, plus 4x cubed minus 5x squared plus 2x dx. we take the antiderivative, negative 1/5 x to the 5th plus x to the 4th minus 5/3 x cubed plus x squared evaluated at 0 and 2. When we substitute our limits of integration in, we get 0.2 as the variance, which means the standard deviation would be the square root of that number. Now, let's go back to this original function. This is a quadratic. It's a quadratic, and if I graph it, we find that it has x-intercepts at 0 and 2, which means the maximum is right there in between it, which we found for the mode. And this function is symmetric. And anytime you have a perfectly symmetric function between the bounds that you're looking for, right here in the middle, when it is exactly symmetric, this is the mean, the median, and the mode. If the distribution is not symmetric, these three numbers won't be the same. But it is always the case that a symmetric distribution has a mean equal to the mode equal to the median. And that can be very helpful when you're not allowed a graphic calculator, which we will see in some other problems.